So hello, I'm Liam Smith. I'm a PhD student in Fabio Scianini's group here. And before I get started on any of this talk that I'm going to say, I just want to say thank you for everyone for staying until the final talk. I realise that the focus might be somewhat tested in the room at this point, so I hope you do find it as interesting as I do, and hopefully I keep your attention until the end. But yeah, I'm going to talk to you today about investigating the work that I do that investigates the effect of environmental and hydrodynamic conditions on CRUD deposition, particularly in PWR simulated environments. I will confess not all of this work is mine either, but this has been a kind of long-standing research project over the past decade or so at the university. Fabio's done a lot of work on this area, and also Michele, who's in the audience, who's my co-supervisor. But hopefully I can go through some of the standout or highlight the results from this work. So yeah, I just want to introduce some of the sort of basic concepts that are around that I'm sure a lot of people in the audience will be familiar with, but just to refresh on those aims of the studies and how we perform these actual deposition studies at the university, and then highlight some of the key findings that really tell the story and summarize all those in an overall deposition mechanism that we see. So, like I've said, what I try to replicate is I focus on PWR water environments, so around about between 200 to 300 Celsius, highly pressurized, so we can keep it as a liquid environment, and we add a certain amount of lithium hydroxide and hydrogen, and also boric acid in the civil industry to mitigate any corrosion or potential corrosion issues around those water circuits. And in particular, what's important here is where the CRUD comes from. So that is it's known to come from the formation of a double oxide layer, particularly on stainless steel components within the primary circuit, that forms this dual oxide layer that you can see here. So we have a passive inner layer that has a high chromium content, and which forms by solid state diffusion from the base alloy. And we have an outer layer that's formed by precipitation, as these iron and nickel metal cations can dissolve or dissolute into the coolant and be carried around the coolant circuits and precipitate back onto the surface of the structural materials like so. So as this iron and nickel dissolves or dissolutes into the surface and is carried with the coolant flow, it can deposit in certain preferential regions, and this is what's always first coined the term CRUD. So it stands for Chalk River Unidentified Deposits, which is where it was first seen in the Chalk River reactor over in Canada. And it can deposit due to various conditions, so we can either have temperature gradients, flow perturbations that cause pressure contractions, heat transfer or boiling mechanisms that happen particularly on the fuel rod surface, or in particular the one that I'm going to focus on today is these regions of accelerated fluid flow. So these regions are encountered when we go through a flow restriction, which is shown on the right-hand side here in various components around the primary circuit and secondary circuit of a PWR. And obviously this is quite bad because in the most severe cases it can cause flow blockage, and that's not what we want in these well-regulated environments. So these corrosion products are thought to deposit in two ways. So we're thought to have they can potentially deposit in a particulate form. So what happens is we get fluid flow that encounters the restriction, we get an acceleration. That increases the kinetic energy of the particulates that's carried. We also get separation of the flow from the structural wall, which creates this low velocity recirculation zone that's at low pressure. Potentially that pressure could be lower than the saturation pressure of the water, and we can get deposition of particulates in these regions, which causes a diameter reduction and can get worse over time. It's also thought that these corrosion products could deposit from a soluble means. So when a metal is immersed in an aqueous environment, we have a reordering of the ions that are in solution, and we get the formation of an electric double layer. The inner layer is the immobile layer of ions that are specifically adsorbed to the metal surface, and we can have an outer layer or a diffuse layer that has these mobile ions that are able to move with their charge. So as coolant flows parallel to the metal surface, we induce a shearing force on these ions, which redistributes this charge and generates what's known as a streaming current. And in regions of acceleration, we can form an excess in this streaming current, which must be balanced somehow. So it's thought that the balancing of this excess current could either be from a back conduction to the fluid, but in low conductivity solutions such as PWR environments, it may not be suitable to sustain that back conduction to balance the charges. So what is thought to happen is we can get the generation of a wall current from the material itself that can support anodic reactions, and in particular, in our case, this one that's at the bottom here. So it can support the oxidation of Fe2+ to Fe3+ in the form of magnetite and form this CRUD deposit on the surface of the flow restriction. Some of the work that's this sort of image in particular was done by one of the previous students here, J.J. Wu, who did a lot of modeling on this phenomena, and she found that if you get the formation of this first deposit on the edge of the orifice, you form new current loops downstream that could form secondary deposits, and you'll get a ripple or a distinctive ripple structure like so as the deposit progresses. So in particular, some of the work that or the aims of the experimental studies that we've done at Manchester look to study how the interaction between the structural material and the environmental conditions occurs. And in particular, the three results that I'm going to talk through today is the effect of the substrate material, pH, and moving on to a new area that we're looking at in alternative alkalizing agents and how they affect this deposition phenomenon. So the way we do that is I work on this autoclave flow loop that's based in the Henry Royce Institute that's just over the road. This has an autoclave at the side here, which you can see as it's open, when it's open, sorry. And we have these flow cells that are inside the autoclave where we can house our samples, and we can specifically look at the deposition process that occurs post-test as well. This sort of photo that I've just taken here can be simplified to a flow schematic where we have a large feed tank of water that we use high purity deionized water. This gets pumped around the system by a high pressure pump, and we usually go to a system pressure of 120 bar to mitigate any potential regions of steam formation or cavitation. It gets heated, injected into the autoclave chamber here, where it's at the target test temperature. In particular, we use 230 degrees, just so we can be sure that we're not forming any steam at any points and we're far away from the vapor pressure. And it goes through this flow cell that's situated in the autoclave itself. And this flow cell houses what we use stainless steel discs with a central microorifice that generates the necessary acceleration in order to promote this deposition process, and we can form CRUD on the surface and in the throat of the orifice disc. After it passes through this sample, it's cooled, depressurized, and we can monitor the flow rate, conductivity, and the oxygen on the return as well. It's worth to note as well that during the test, we can track the diameter reduction of this orifice by monitoring the flow rate and the pressure drop across the orifice. And we rearrange these equations, and we can track the diameter reduction over time that would be due to this deposition process that's happening on the surface of the stainless steel disc. So in particular, just looking at some of the effects or the highlights of this work, the first one is the effect of the substrate material. So there was a study done by a predecessor of mine, Stefano Casanere, who looked at the difference between electrically conductive surfaces and insulating surfaces. So in particular, in this case that I'm showing alloy 690 and a zirconia sample. And he found that in high purity water with a high temperature pH of around 5.6, there was no significant difference. So there was a similar morphology and a similar diameter reduction in these conditions. Once he increased this pH to 7.6 with the addition of lithium, he found that for the conductive samples, so stainless steel and alloy 690, this diameter reduction was completely eradicated, and it was left with a highly ordered deposit in the proximity of the orifice edge. But moving to insulating samples, no deposit was seen. So this is kind of the first indication that we've seen or that's presented that shows that the generation of this wall current from the surface may be able to sustain this oxidation process and form this magnetite deposit around the orifice itself. But in the literature and in the work that we've done here, we found that the effect of the pH, or the pH has the greatest effect on this deposition process. So like I've just shown there, but once again, in high purity water, we get this diameter reduction in this particulate deposit that forms around the orifice. And once we increase this pH, irrespective of the concentration of lithium hydroxide that we add to increase the pH, this diameter reduction is completely eradicated, and what we're left with is a surface deposit around the orifice. This surface deposit increases in crystallinity or order and becomes shorter as we increase the pH. And it's thought that the eradication of this diameter reduction and the reduction in the deposit is due to the decrease in solubility of iron and nickel within the two water chemistries, or as the pH is increased, I should say. So what I've been looking at recently is moving on to alternative alkalizing agents. There's various drivers for this. So Western PWR designs were mainly based on lithium hydroxide, but with the price of lithium ever skyrocketing these days, companies are looking to switch over to potassium hydroxide as an alternative counterpart. And some of the preliminary studies that we've seen is that at the equivalent pH and equivalent flow velocity through the orifice, we see a very, very similar deposit again. Again, this same highly ordered deposit in the proximity of the orifice edge is shown. And the composition measured via Raman is pretty much equivalent as well. We can see that in the outer surface, we get this strong magnetite peak. And then in the CRUD deposit, we get a hematite peak here, but this is most likely due to a laser-induced transformation of magnetite into hematite that's known in the literature. We shouldn't really be getting any hematite forming because the oxygen concentration that we have during our tests is around 1 ppb. So this is sort of a known process, but all to say that between the two pH razor environments, we get pretty consistent morphologies, position of the deposit, and the composition as well. So, but moving on to looking at what the surface buildup rate is. So the way we do that is a post-test analysis. So this data plot here was published again by Stefano in lithium, various concentrations of lithium. And this surface buildup rate was calculated by laser confocal microscopy. So he did an image in the X and Y plane of the surface and also the Z plane to measure the volume of the surface deposit, divided this by the total test time, which in our case is 100 hours, and that gives a buildup rate for this surface deposit. So when I initially started moving on to testing potassium, I wanted to test to make sure that my tests in lithium were equivalent, which they were, which is this pink square here, and also some preliminary tests in potassium. I did this green one here before we moved the flow loop over at the very start of my PhD, and I was happy with the repeatability of these results with previous work. So then I expanded this velocity study and tested more velocities and tried to get this. I'm still expanding this range as we speak, but these are some of the first results that we've had. But all to say here that on the whole, the buildup rate in potassiated water chemistry is decreased relative to the lithiated water chemistry. And we can see that here when we look at the circular profiles that are generated, and this time from white light interferometry. So these are generated, so we have a 3D image of the surface deposit here, up here in lithium, and this in potassium. The dashed line around the orifice is to show where we take a circular profile. What we then do is we average the Z values along this circular profile. We go 2.5 microns out, and we do exactly the same again. And that's what all these squares are shown on this profile here. So what you're seeing is an average build-up height in the blue, which is potassium, and the red, which is lithium. So what we can see here, that on average, the surface deposit height, and hence the build-up rate, is reduced at this one flow velocity by on the order of around about 6 microns in potassium when compared to lithium. So this could be rationalized by the increase in conductivity of the bulk fluid when we test potassium. So in potassium, we have a conductivity of around about 78 microsiemens per centimeter, whereas in lithium, it's 68 microsiemens per centimeter. So we have around about an increase in 10 in the conductivity at room temperature. So what we could be doing here is negating the need or promoting the back conduction to the fluid of this excess in charge and reducing the extent of the wall current that drives this oxidation and the deposition formation. But this is very much a work in process. There's more data points to be added, so it's a watch this space for this sort of study. So overall, what do we see? Well, in the absence of an alkalizing agent, so we're just in high purity water, we can see that the CRUD deposit and morphology is dominated by particulates. When we increase the pH, and particularly when we increase it above pH 7, we can see that this is left with a surface deposit. And we've indicated the presence of an electrokinetic deposition mechanism by, one, the need for a conductive surface in relatively high pH environments. The fact that, well, I should have mentioned that there's some modeling work done by an engineer at Rolls-Royce called Andy Banks. He was a great engineer. Unfortunately, he's retired now. But he did a lot of this early modeling work that's shown that the streaming current generation changes with the flow velocity to the power of 9/5 or 1.8. What we can see from the experimental work here is that the build-up rate varies with velocity to the power of 1.73. So pretty close, and they're in good agreement there. And also, the fact that these more recent results have shown that an increase in the solution conductivity when we move to potassium decreases the CRUD height overall, and hence the build-up rate. So that also indicates that we're reducing the wall current effect in these regions. So along with these, and just moving on to some of the future work that's going to be done in this area, along with the conductivity studies like I've mentioned, we've recently taken delivery of a new flow loop that was built and constructed by a Finnish company, Cormit Testing Systems. This will be able to scale up these studies from the kind of micron scale that we see in the orifice discs here to more millimeter scale, so better replicating plant conditions and studying this process around orifices that might be encountered in actual plants. And also in this autoclave that's underneath the insulation here, there's also, we can put a central heating rod in the middle, and we can basically boil various materials, particularly looking at the deposition that's formed on fuel rods, and we can see what happens under boiling conditions, just to see if there's any differences, again, in the different water chemistries that we use, and in expanding our understanding of this CRUD deposition mechanism. So with that, I'd like to thank you for your attention, and I'd be happy to take any questions, please.